All right, we're now ready to move into the first physics content portion of the course. We're going to talk about motion. And before we can talk about the motion of an object, we need to agree upon definitions for the terms that we're going to be using. And so we are going to start in one dimension, and then we'll eventually take this one-dimensional treatment of motion and we'll expand it to 2 or 3 dimensions. So when we talk about motion, what are we referring to? Well, some basic questions that you can ask about an object. Where's the object located? Where is the object going? And how long is it going to take to get there? And so to answer those questions, we need to set up a very formal system with definitions for things like the position of an object. So the position of an object is where an object is located. But to specify a position without any ambiguity, we need to do 3 things. We need to assign a coordinate system, and we're going to talk a little more about coordinate systems in this video, but first we need to assign a coordinate system. And the nice thing about assigning a coordinate system is that literally it's up to you. You have the choice for whatever coordinate system you want to assign. Once you've set your coordinate system, you need to, along with the coordinate system, define a reference point, and often this is referred to as the origin. And so you have a coordinate system with an origin, and then to specify the position, you need to specify how far from the origin the object is located, and in which direction from the origin is the object located. And you can see these 2 things are exactly the information we need if we're dealing with a vector. There's a magnitude or a size, and then there's also a direction. And so position is a vector. The SI unit for the position is a meter with the symbol m. So a typical position variable in one dimension, horizontal motion, typically we would use x. For vertical motion, y. And then if we have a 3D problem, that 3rd dimension, typically we'll assign as the z variable. If we're dealing with all 3 dimensions at once, then the position vector is essentially just the sum of the x position plus the y position plus the z position. So over here on the right, I've got an example. I've got an x position vector of plus 6 meters. And here, notice that I'm using my unit vector notation. And so I've got a coordinate system drawn down here. I've got my horizontal axis. I've got my x with the plus sign designating to the right as plus. And so my position vector, plus 6 meters, that means I need an arrow pointing 6 units to the right. And so that is a position vector. So the position vectors are always from your origin, pointing with length the size of the position, pointing in the direction corresponding to the direction of the position. So motion is essentially how does the position of your object change with time, right? So the simplest type of motion would be an object is at a specific position, and with time it just stays there, right? So the object, sometimes we would say that object is not in motion, but really that's just the simplest type of motion where the position is not changing. So the first thing that we want to define for looking at changing positions is something called the displacement. The displacement is the change in position. And so if I was going to write out the x displacement, I would write out this expression right here, this delta x, so delta meaning the change in, so final position minus initial position. So subscript f here is final, subscript 0 is the initial position. And so the displacement is the change in the position, comparing the final position of an object to the initial position. And so in 1D, typically for horizontal displacements, you might have delta x. For vertical, you might have delta y, and for in and out of the page, perhaps, you might have delta z. And then the displacement in 3D is just the sum of each of those three displacements. So let's look at an example down here. I've got an initial position of 6 meters, plus 6 meters in the x direction, and so that's my purple vector here. And then I've got a final position of plus 10 meters in the x-hat direction, so that's my blue vector right here. And so the displacement is defined as x final minus x initial. And so here I've written out x final minus x initial. Well, remember, subtracting a vector is the same thing as adding the negative of that vector. And so I've got my plus 10 meters for my final. I've got my minus 6 meters. Notice how both of these are in the x-hat direction. So x initial is plus 6 meters in the x-hat direction, but since I'm subtracting, I've got negative 6 meters in the x-hat direction. And so when I put those two together, I get plus 4 meters in the x-hat direction. So what does that mean? It means my position has changed by a total of 4 meters, and the plus sign, or the plus x-hat, means that the position at the end, the final position, is 4 meters to the right of where I started, and you can see I've drawn in the displacement vector on this figure. This is your delta x vector. All right, so let's look at some applications for displacement. The first thing we want to point out is that position, which is dependent on your coordinate system that you've adopted, position is arbitrary, but displacement is not. And we're going to look at an example here that demonstrates that. So first, in this figure, we've got a lot going on, so just pay attention to this part first. So I've got a person standing at this location, and then at the end of the motion, the person is going to be standing over here. Right, so initial location, final location. And what I've got up here and down here, so in the red and the blue, are two different coordinate systems. So in the red coordinate system, so this is the location initially. So in the red coordinate system, that corresponds, that initial position is plus 12 kilometers. And so you can see down here, my initial x position is plus 12 kilometers. Now, I'm at the exact same location in the blue coordinate system, but you'll notice that I've actually set my origin way over here, and so my initial position in the blue coordinate system is minus 8 kilometers in the x-hat direction. So in the red coordinate system, initial position is 12 kilometers plus 12, and in the blue coordinate system, the initial position is minus 8 kilometers. Right, so the positions are not consistent between these two coordinate systems. And then at the end, so here's the location final, in the red coordinate system, that final position is 0, so 0 kilometers. In the blue coordinate system, this location right here is negative 20 kilometers. So again, we disagree about the initial position, we disagree about the final position. But let's look at the displacement. Now remember, the displacement is delta x is x final minus x initial. So in the red coordinate system, that works out to be 0 kilometers minus 12 kilometers. So I end up with a displacement of negative 12 kilometers the x-hat direction. So that's 12 kilometers to the left. In the blue coordinate system, my final position is negative 20 kilometers. My initial position is minus 8. So when I plug that into the displacement expression, I get negative 20 plus 8, and I get negative 12 kilometers in the x-hat direction. So even though the initial positions are different, the final positions are different, as long as you've done it correctly, the displacements across coordinate systems should be exactly the same, right? Because that's corresponding to a change in position, and the changes in position, that is essentially set by what happens in the motion. It doesn't actually matter what grid I put down and what I number things. All that matters is that the position has changed, and in this case that displacement was 12 kilometers to the left, or negative 12. So one thing we want to point out is that if you have multiple displacements or multiple changes in position, let's say you've got an object that moves to the left and then moves to the right and then moves back to the left, the total displacement is just the sum of the individual displacements. So you're just going to add up each displacement over the entire motion. And so let's look at an example of that. So let's say that my first trip, my displacement was just 2 meters to the right. And then I pause, and then I take, say, 5 steps back to the left. So my displacement in the second trip is negative 5 meters. Then I pause, and I take another trip to the right plus 7 meters. So if I want to know the total displacement of my trip, comparing where I ended up at the complete end of all 3 journeys to where I started, I'm just going to add up each of the individual displacements. So I've got plus 2 meters in the x-hat direction, minus 5 meters in the x-hat direction, and then plus 7 meters in the x-hat direction. And so when I add those up, I've got 2 minus 5 plus 7, that's going to add up to plus 4 meters in the x-hat direction. So after all of that travel, I end up 4 meters to the right of where I started initially. So one important thing to point out is that this is referring to the total displacement. An interesting question to ask is, how does that compare to the total distance that you traveled? And the distance traveled, essentially, distance doesn't take into account direction. All that matters is tracking the total change in location over the entire trip. And so the distance traveled in the first portion was 2 meters. The distance traveled in the second was actually just 5 meters, right? There's no taking into account that we're walking back to the left. You still walked 5 meters. And then that third trip was 7 meters. And so when you add these 3 up, you end up getting 14 meters total for the distance traveled. Okay, now that we've defined displacement, which of course is taking into account the change in position, the logical next question to ask, at what rate is the position changing? Right? If we're interested in modeling the motion of an object, then we want to be able to characterize motion where the position, in 2 cases, if the position changes by 5 meters, but in one case that happens in 1 second, and in another case that happens in 1 hour, that is different motion, and we want to be able to characterize that. And so this is introducing us to the idea of velocity. And so we're going to start with the average velocity, the definition. And the average velocity is just the ratio of the displacement divided by the time interval over which that displacement happened or occurred. And so the average velocity is a vector. The direction of the average velocity is the same direction as delta x. You'll notice here that delta t is a scalar, but delta x is a vector. And so the direction of the vector for average velocity is the same direction as the displacement. The SI unit for velocity is meters per second, right? A length unit divided by a time unit. And so let's look at this example here. Let's say that we walk in the x direction for 8 seconds and we go 4 meters, right? So we cover 4 meters, 8 seconds, and we are traveling in the positive x direction the entire time. So that means our displacement is going to be plus 4 meters in the x-hat direction. Our time interval is 8 seconds. And so when we take that ratio, our average velocity is 0.5 meters per second in the positive x-hat direction. Now, let's say we turn around and we walk in the negative x direction, we go 2 meters in 2 seconds. Now, what's our average velocity during that portion of the motion? Well, our displacement is going to be negative 2 meters. We walked back to the left 2 meters, and we did that in 2 seconds. And so our average velocity in interval 2 is negative 1 meter per second in the x-hat direction. The negative here corresponds to we're moving to the left rather than to the right. And so 3 here, what is our average velocity over the entire 10 seconds? Right, we just calculated over the first 8 seconds and then the next 2 seconds, but what about over the entire 10 seconds? Well, first off, what's the total displacement that we traveled in that 10 seconds? Well, we already said that the total displacement is just the sum of the individual displacements. So plus 4 meters and minus 2 meters, so my total displacement is just plus 2 meters in the x-hat direction. The time interval, well, it's 10 seconds. And so the average velocity over the entire trip is plus 0.2 meters per second in the x-hat direction. And so how do you interpret what the average velocity, what information is that providing you? It's essentially telling you that if you traveled the entire 10 seconds at 0.2 meters per second in the plus x direction, if you traveled the entire 10 seconds at that velocity, you would end up 2 meters away from where you started. Now, of course, that's not the actual motion. We traveled for 8 seconds at 0.5 meters per second to the right, and then we traveled for 2 seconds at minus 1 meter per second to the left, or 1 meter per second to the left. And so the average velocity, although it provides you with some general information about the motion, it can gloss over or omit some of the details that we might be interested in if we're trying to characterize the motion. In particular, if we want to know the velocity at a specific instant, the average velocity often will not be sufficient to provide us with that information. And so that introduces us to this second idea of velocity, the instantaneous velocity. And the instantaneous velocity is really what we think of or are referring to when we say velocity. And so velocity will be sort of used for most of the course. And when we use that, we're referring to instantaneous velocity. So the instantaneous velocity, if you look at this definition here, it's the limit of the time average velocity it's the limit of the average velocity as the time interval approaches 0. And if you've taken a calculus course recently or even in the past, you should recognize that language as the interval approaches 0. That sounds like calculus speak. That's actually a derivative. And so the instantaneous velocity is the derivative of the position vector with respect to time. And so v of t, x of t, our position and velocity vectors are functions of time. And this is essentially the idea of motion. We want to see what happens to the position as time evolves. We want to see what happens to the velocity as time evolves. And so these functions are functions of time. Okay, so let's take a moment to make sure we're careful with the language that we use going forward. We've been talking about average velocity and velocity, which are vectors. What's the difference between velocity and speed? Well, average speed takes into account the total distance traveled rather than displacement and divided by the time interval. So the average speed, just take into account the total distance traveled, divide that by the total time, that's your average speed. Your instantaneous speed is essentially the magnitude of the instantaneous velocity. So whatever your velocity is at a given instant, your instantaneous speed is just the magnitude of that velocity. All four of these quantities have the same base unit, or the same units, right? Meter per second. You may see kilometers per second, kilometers per hour, miles per hour, but all of those quantities have the exact same unit. So let's take just a moment to consider graphically what all of this means. And so what I've got drawn here is a position versus time graph. So I've plotted this black curve here is just the position plotted as a function of time. So some object is in motion. I've just made this up. And we're going to investigate what we can learn from looking at this black curve. So the first thing, if we just read off the values on the y-axis, that's going to tell us the x position, right? So here at time t1, right here, x1, that's the position of my object at time t1. And then if I want to know, well, where's the object at t2, I just read off that value. So let's consider t1 and t2. That's two different times. If I compare the position at those two different times, then I can determine the average velocity or the average speed of the object just by determining the slope between those 2 points. And so if you take into account the plus or minus value of the slope, then that plus or minus will correspond to the direction for your velocity. If you just look at the magnitude of the slope, then that's going to be the average speed. Take into account the plus or the minus, that'll give you the average velocity. And so when you take two distinct points and calculate the slope between them on a position versus time graph, you're going to get information about the average velocity. Now, what about instantaneous? Well, for instantaneous, rather than taking a time interval, we're going to just select an instant in time, t3. And we want to know what's the velocity at that instant. Well, that corresponds to the slope of the line that's tangent to that point. And so this is where the derivative comes in. You're taking the derivative, which gives you the slope of the tangent line. And tangent meaning that it just passes through that 1 point. And so the slope of that tangent line gives you the instantaneous velocity if you're taking into account the plus or the minus of the slope. And if you just take the magnitude of this slope, then the magnitude will be the instantaneous speed of the object. So again, this is for a position versus time graph. If you look at the slope between any 2 points, that'll give you the average velocity information. And if you look at the slope for any line tangent to a specific point, that'll give you the instantaneous velocity. Right? So position versus time, you're thinking about slopes to tell you something about the velocity. All right, we brought up the idea of velocity and speed when we were exploring when the position changes or the displacement. And so the next natural question to ask is, what about if the velocity is changing? What physical quantities does that correspond to? And so that brings up the idea of acceleration. The acceleration is the rate at which velocity changes. And so just like with velocity, we can first talk about average. So the average acceleration of an object is just the ratio of the change in the velocity divided by the change in the time interval for which it happened. And again, delta meaning v final minus v initial, right? Or t final minus t initial. Now, this is an incredibly important point right here, so I'm going to really highlight this. The acceleration vector points in the direction of delta v, the change in the velocity. This is not necessarily the direction of v at a given instant. So what we care about for this average velocity is how the velocity is changing, not necessarily the direction the velocity vector is pointing. Now the SI unit for acceleration, well, I've got meters per second and then divided by seconds. So my unit is meter per second squared, or what I just said, meters per second per second. So if we want to know how the velocity is changing at a given instant rather than over a time interval, then again we need to adopt an approach from calculus, and we need to take the time derivative of the velocity vector. And so instantaneous acceleration we get by taking the derivative. The average acceleration we get by looking at the change in the velocity divided by the time interval. So let's look at this graphically as well. Here, instead of a position versus time graph, I now have a velocity versus time graph. And so you'll see I've got this velocity curve. Again, I just made this up, but some object is in motion, and if you want to read off what the velocity is for the object, all you got to do is just pull off the vertical values here. Those correspond to the velocity at different times. And so first, let's just look at time t1. All right, the velocity is this v1 value. Notice how I'm below the origin here, and so this v1 velocity is actually negative. I don't have numbers on there, but be some negative velocity. My t2 corresponds to this velocity, so the velocity at the second time is now positive. And if I want to talk about the average velocity between these 2 points during that time interval, then I'm just going to calculate the slope that connects these 2 points. So the slope between those 2 points is going to give me the average acceleration during the time interval t1 to t2. So that is the average acceleration. Now, if I want to know the acceleration at a given instant, I can't look at a time interval. What I need to look at is a specific instant in time. And just like with the previous example, if I take the slope of the line tangent to my velocity curve, so right here, that slope corresponds to the instantaneous velocity. So taking the derivative at that location gives me a line with that slope, and that corresponds to the instantaneous acceleration for this particular object. Notice that just looking at the curve, you can immediately determine roughly what the acceleration is for the object down here. The object is almost traveling at constant velocity. This is almost horizontal, and it's negative. So the object's traveling to the left, say, if it's horizontal motion, traveling to the left at a constant velocity, and then gradually, notice what's happening here, gradually the velocity changes and actually crosses zero. So the velocity is negative, but the velocity starts to get smaller and smaller in magnitude. That's because the object is accelerating, it turns out, in the opposite direction, in the positive direction. And we know the acceleration is positive because the slope everywhere here is positive. And so the slope is positive, so the object's accelerating. We've accelerated up to this, whatever this velocity is. And you'll notice here it seems like the acceleration stays constant. The slope doesn't change much. And so we're increasing in speed up to some value up here. And then the velocity levels off, and it looks like we essentially start traveling at a constant velocity, very high magnitude, right? Much further up on the axis than v2. But now we're traveling at a constant velocity. Now this is a positive velocity, so we'll be traveling to the right. But the slope here is roughly zero. That corresponds to zero acceleration or constant velocity. So when you have your velocity versus time graph, you can immediately pull out information related to the acceleration just by examining the slope of the curve.